Thank you.
Okay, I believe it's time for the next participant. So it's Dmitry Fedorov, Dr. Fedorov, who is also from Variational Laboratory.
Hello, everyone. Let me share my screen. So today I'm going to talk about the ab initio molecular dynamics on a quantum computer, and also with a quick introduction to ab initio molecular dynamics, where we solve the time-dependent Schrödinger equation for the total molecular wave function that depends on the electronic coordinates, nuclear coordinates, and time. And to begin, we start with the time-independent problem, solve time-independent Schrödinger equation. Here on the left, where we have kinetic energy of nuclei, kinetic energy of electrons, interaction of electrons, potential energy of the interaction of the nuclei, and the interaction of electrons with the nuclei. And so to solve this equation, the perhaps most common approximation is the Born-Oppenheimer approximation, which separates electronic and nuclear motions, taking advantage of the fact that electrons move much faster than the nuclei, and it assumes that electrons adjust instantaneously to the changes in the position of the nuclei. And so we are able to separate these electronic and nuclear wave function, which simplifies our problem. And here we have the electronic Schrödinger equation, so where the eigenvalues of the electronic Hamiltonian are represent the potential energy surface on which we can propagate the nuclei. And when we solve for nuclei in this particular way of ab initio molecular dynamics, we assume that nuclei move classically, so the Planck constant is 0, and we end up with simple classical equations for the propagation of the nuclei. And to run these simulations, what we basically need from the electronic Hamiltonian is the energies and the forces. So how do we do this on a classical computer? So quantum chemistry deals with these kind of problems where we find the approximate solutions, where one would usually begin with like a mean field method like Hartree-Fock, which is basically assumes that the electrons moved in the field created by all other electrons, and is represented by this lowest energy electron configuration, which recovers most of the energy, but all the interesting effects are in the rest of the energy, which is called the correlation energy, where there are contributions to the wave function of excited configurations. And so these are post-Hartree-Fock methods such as coupled cluster, configuration interaction, different multi-configurational methods, and full configuration interaction, which is exact for a given basis. But the problem is that this kind of approaches are the number of possible electronic configurations grows exponentially with the system size. So how can we leverage the quantum computers for that? So when we deal with classical bits, we have 2 states, 0 and 1, for n bits, 2 to the power of n possible states, and our system is always in one of those states. So on a quantum computer, quantum bits are, we have 2 to the power of n possible states, and it can be in a superposition. And this is a perfect possibility to use the quantum computer, where you can actually represent a quantum system on a quantum system, really. So we have our molecule here that we need to simulate. We map the state, prepare the state on a quantum computer, and then using some unitary operators, we evolve this system and perform the measurements. And this has a potential of solving problems that are intractable on classical computers, because, for example, to simulate 50 qubit system requires 16 petabytes of storage just to store the amplitudes. So quantum chemistry and quantum computers. So we begin with the electronic Hamiltonian in the second quantized form, where here we have two terms. Here HPQ is the one electron integrals, and HPQRS are two electron integrals, and A and A dagger are creation and annihilation operators. And so electrons are fermions, which we need to map on, which are indistinguishable, which we need to map on qubits, which are distinguishable. There's multiple ways to do that, but the resulting Hamiltonian is always of this form, where we essentially have the sum of these the polystrings with the coefficients in front of them, and each polystring is a simple product of the poly matrices. And the method we use for simulations is the unitary coupled cluster, which applies this unitary operator to construct the trial wave function. It is a modification of the common in quantum chemistry method that run on classical computers, the coupled cluster method. And here we basically, by doing these excitations, where we introduce the electron configurations, singly excited and doubly excited, and this method is called unitary coupled cluster with singles and doubles. And the goal is to find the ground state electronic energy. So since quantum computers are still in its infancy, we can't really solve it completely on a quantum computer, just because the coherence times are not long enough. And the common approach nowadays is the VQE, where we start with a fermionic Hamiltonian, map it to qubits, generate initial state, prepare it on a quantum computer, solve, measure the energy, and in a self-consistent fashion, using classical optimization loop, we find the minimum of the ground state energy, which according to using the variational principle. So this is a quantum classical approach. So that was energy. So we also need the gradients to run molecular dynamic simulations. And in this work, we calculate the gradients numerically using the Hellman-Feynman theorem and finite differences. So the expression for force looks like this. We essentially don't recompute don't optimize the wave function at the displaced geometries, and we neglect these two terms, which are called the Pulley error. And so this is the final expression for the numerical gradient. And so for each molecular dynamics time step, we run VQ optimization to obtain energy, calculate two matrix elements to get forces, and propagate the positions and velocities. So if we begin with the brute force approach, where we calculate, if we calculated the energies at the displaced geometries the same way as at the central point. So we basically run 3 VQ loops for each geometry. And here in the center, we would have to run a number of measurements equal to a number of iterations of VQE multiplied by the number of shots for each circuit measurement. And for displaced geometries, we would need to do it, displace it in every dimension. So the number of the measurements would be 6n times number of iterations and number of shots. And so, which would obviously increase with the system size. When we apply the Hellman-Feynman theorem, things starting to get cheaper. So we do not optimize the wave function at displaced geometries. We simply use these coefficients theta to measure the energy at the displaced geometries and calculate the classical 1 and 2 electron integrals. So this gives us a speed up. We don't have to run multiple whole VQE cycle at the displaced geometries. And so when we calculate the numerical gradient, there is the obvious problem is that this displacement parameter D, to get accurate gradient, it has to be a small number on order of 10 to the minus 3, 10 to the minus 4 to get the accurate value of the gradient. But when you have errors in energy at displaced geometries, because you measure energy on a quantum computer and there is some uncertainty in that, and these errors are not correlated, and we get quite large error amplification in terms of the gradient. So what we're doing in this work, we use the correlated sampling technique, which instead of doing the measurements at displaced geometries, we simply take the measurements from the central point and use it for displaced geometries, and only recalculate the classically electron integrals, which what it does essentially is the errors at displaced geometries are correlated now, and so they are not independent, and that should improve the accuracy of the gradients. And so the reason this works is that for different geometries, we don't have different polystrings. The only difference is that we have different coefficients alpha, which depend on the electron integrals. And so we measure our quantum circuits only once at this central point, and only recompute the classical integrals. And this basically doesn't increase cost on a quantum computer. There is only extra calculations on a classical computer. So this can work for larger systems because we don't have to do displacement in every direction. So the simulation types we run is the simplest one is the state vector simulator, where we, instead of doing quantum measurements, we simply read out the wave function, and there is no stochastic noise that you get when you do the quantum measurements. And this essentially simulates perfect hardware with a limited number of shots, infinite number of shots. On a QASM simulator, we get stochastic noise due to the quantum probabilistic nature of quantum mechanics, where the wave function collapses to one of the possible states, and we need to run this multiple times. And this is the expression for the number of shots, basically to get the number of shots is inversely proportional to the inverse square root of the accuracy that you want. And in simulations on hardware, in addition to stochastic noise, we add noise from quantum devices, which is at this moment in time is quite large. And to do this on larger systems, we need error mitigation. So we tested our approach on the H2 molecule using the Qiskit package for simulations on a quantum computer, and PySCF for classical quantum chemistry simulations. We used the unitary coupled cluster with the minimal basis set. And for H2, where we only have 4 spin orbitals, this approach is equivalent to full CI. We use the parity mapping, which allows us to take advantage of the symmetry and reduce the number of qubits that is required for a calculation from 4 to 2. So 4 is the number of spin orbitals, and it maps to 4 qubits. And using symmetry, we get a 2-qubit system. And additionally, we're using the qubit tapering method described in this paper, where using even more symmetries, we can reduce the number of qubits to 1. So we have this 2-qubit system over here, and 1-qubit system that we're going to run simulations on. So we begin with energy calculation using a QASM simulator, where only stochastic noise is present, using different number of shots for each circuit measurement. So these are the errors of energy along the potential energy surface for different internuclear distances. And these black dashed lines are chemical accuracy, which is around 1.6 millihartree. And to be consistently within chemical accuracy to get the correct energies, we need at least 256,000 shots out of this set. So this is the number of shots that we need to get the energies within chemical accuracy. So the next thing is we need to pick the parameter d, the displacement, to calculate the numerical gradients. So here is the gradient curve, and this insert is the error of the gradient using the state vector simulator. So there's no stochastic noise. This is computed for different values of d. And as you can see, the errors are on the order of 10 to the minus 3 millihartz per Bohr, and it is worse for larger d, but it is still quite a small number compared to what we get when we do a QASM simulator, when we add stochastic noise. And here error jumps by 3 orders of magnitude. And here, as you can see, the value d doesn't really affect the gradient accuracy because energies are correlated because we use the correlated sampling technique. And this is the root mean square error along the potential energy curves using different d parameters. And there's no correlation between the parameter d and the accuracy. So basically the stochastic noise is much larger than the error we get from this numerical calculation of gradient. So the actual simulations we ran on IBM quantum hardware on a 5-qubit Vigo machine, which has the lowest error rates for our particular problem. So we ran this trajectory starting at the internuclear distance of 2 Bohr with 0 velocity, and we can show the trajectory for this one-dimensional system using this plot of velocity versus position, where you get this loop if your closed loop if your calculation is accurate enough. So here the orange curve is the state vector simulator, which is essentially exact solution. The blue line corresponds to the simulations where we run full VQE cycle optimization for each geometry. And for comparison, we show this green curve, which is a trajectory run using the optimal theta parameters that are optimized with state vector, just to see how what is the difference between the full VQE optimization at each step versus running a trajectory with optimal parameters. And here you can see that this looks pretty good. So we after a single loop, we end at the same point. And this is the total classical energy conservation plot. So the energy oscillates by around 256 millihartry, which is not within chemical accuracy, but it doesn't seem to drift. It just oscillates due to the noise from the quantum hardware. So this is a quite elementary circuit with only 1 qubit and 3 gates. We also ran simulations using a 2-qubit system, which is shown here. So again, the green line is what you saw on the previous slide for 1-qubit system, and the red line is the 2-qubit system. As you can see, we get this, we significantly overestimate potential energy across the trajectory, and the classical energy conservation is not necessarily worse. And you see this deviation on the trajectory for the 2-qubit system from this, from the state vector simulator. And this is due to the fact that we add extra gates, and mostly due to these CNOT gates, which are on this hardware. Each of them has an error rate of around 1%. And this is the result we get due to those errors. And obviously, if we want to make this better, we need some error mitigation implemented, but that's possibly a direction of future work. So the last thing I want to talk about is how our approach can scale to larger systems, because we only ran this for H2. So we need to eliminate errors from the VQE parameter optimization and variational ansatz not being exact to look at the larger molecules. And actually, see what the error comes from us using Kalman-Feynman with correlated sampling approach. So what we do is we do exact diagonalization at central point to get the exact wave function for these molecules. Different number of qubits represent to the cases where we use or don't use the symmetry to reduce the number of qubits. And so after we do this exact diagonalization, for each polystring, we sample these matrix elements using the exact wave function. And we sum all those matrix elements to get energies and compute gradients. So here, the blue is the brute force approach without application of Kalman-Feynman theorem or correlated sampling. The red one is where we apply the Kalman-Feynman theorem, but no correlated sampling, and the green one is when we apply correlated sampling technique. And these are the number of shots to reach 1 milliharship per Bohr accuracy. And as you can see, there is no difference between the brute force and Kalman-Feynman approaches in terms of shots required to reach this accuracy. We just reduce the number of calculations we need to do because we don't re-optimize the wave function at displaced geometries when we use Kalman-Feynman. And most importantly here, the green arrows represent the correlated sampling technique, which allows us to reduce the number of shots required to reach this accuracy by 3 or 4 orders of magnitude. And with that, I'd like to conclude. We presented the method to calculate accurate numerical gradients on modern quantum hardware using Kalman-Feynman theorem and correlated sampling. It allows us to significantly reduce number of measurements by orders of magnitude to achieve the same accuracy as a standard finite differences approach. We ran simulations on actual quantum hardware using the VQ algorithm, which calculates electronic energies on quantum hardware. And larger molecules would require more qubits and additional error mitigation. And the last thing, we applied the correlated sampling to VQE, but potentially it can be used to calculate gradients using other algorithms where electronic wave function is available. For example, quantum phase estimation algorithm. And I would like to say thank you to my advisor Yuri Alexeyev, our collaborators from Oregon National Lab, and the for feedback for our coworkers from General Atomics. And if you are interested, the results of this work can be found in a preprint on our archive. And I would like to take any questions. Thank you.
Yeah, thank you very much, Dmitry, for a really interesting talk. Yeah, so it's time for questions. Okay, maybe then I ask one. So you said that you need better quality of qubits to simulate larger molecules, right?
Yes.
So how do you think, is it possible to use this state-of-the-art simulator, which is developed by Dr. Alexeyev, and use some, I don't know, special circuits to simulate larger molecules, which cannot be simulated with some classical methods?
Yes, up to roughly 50, 60 qubits, you can do that. And it's actually quite important in this stage, but eventually when we want to simulate larger molecules, there is no way we can get a classical simulator because just a water molecule with slightly bigger basis set can get to that 50 qubits threshold, and you can't surprise anyone nowadays by doing calculations on water molecules because
that's correct. So we're doing right now still 3G basis set, which is obviously very small basis set. You really want to go 631G star or even larger basis sets. That will require a lot more qubits. The largest we can do probably maybe 40 qubits on a supercomputer. And we have a couple of ideas how to develop a simulator, which actually should be around at least 40 qubits, maybe more. And this is still kind of like work under progress. It's still underway.
Yes.
I have a question, if I may.
Thank you.
At the beginning, you said that they use for H2 was
so because so all configurations are covered by double excitations, single and double excitations, which coupled cluster fully represents. If we add another electron, the coupled cluster would not use
yeah, but I mean, if you use STO3J, I mean, if you use something like a good Popel basis set or something, I mean, the heck of a lot more.
Yeah, so
actually, so you'll have to have a much bigger Hilbert space, and even H2 will just kill you.
Yeah, I had that on my slide. It's like quantum chemists usually don't always say that, but it's always exact in the given basis set.
Yeah.
Obviously, if you
so there's another problem then that most people talking about the chemical accuracy in this context don't mention. I mean, they're talking about the accuracy given relative to their own basis set, not to a real full-scale, full CI, exact calculation.
Yeah, the more, obviously, the bigger the basis, the more energy you're going to recover, yes.
Because when you compare with real chemists, they kind of have different criteria. So they mean by chemical accuracy, they mean chemical accuracy. And then you need large basis sets.
Yes.
And then you have to compete with very big calculations, actually. But anyway, I'll talk about that tomorrow.
Yeah.
Yeah.
Any other questions?
Okay, if not, I'd like to thank Dmitry once again for your great talk. And I want to say that thank you all. So today we had a pleasure to hear very interesting talks. So tomorrow we'll continue the quantum computing in its application section and then move forward to some exciting experiments in quantum physics. So we look forward to see all of you tomorrow here at this Zoom room. So you can use the same link. And thank you again. And we see you tomorrow.
Bye-bye.